Okay. All right. So what I'm talking about tonight are exploding stars, the universe, and you. So what are exploding stars? What causes them to explode? And how they're important for the universe, or our understanding of the universe, and how they're important in your personal lives. All right. So the quick. I will tell you what I'm going to talk about before I talk about it, and I'll summarize it again at the end. So I'm talking about supernova, also known as exploding stars. So those two terms are synonymous. And some of the main points about exploding stars, about supernova, first of all, they're factories for neutron stars and black holes. As far as we know, they're the only way that these two types of entities are formed within the universe. Definitely the only source of neutron stars, maybe black holes. You know, there could be some weird ways that they might have formed in the universe, but we think that the supernova are the only way that they occur. More importantly for you, basically all the elements that make up your body, with the exception of carbon and oxygen and hydrogen, came from supernova. So all the iron that's in your blood, all the calcium that's in your bones, all those like little trace elements, most of that came from supernova, with a few special exceptions. Some of the things like copper and gold and stuff like that also come from merging neutron stars, but I say that those still kind of come from supernova because we need supernova to make them neutron stars in the first place. And then finally, the thermonuclear supernova, a specific type of supernova, give us information about dark energy. So that's the universe part, is understanding how our universe works by observing specific type of supernova. All right, so what we're going to do tonight is follow the story of three stars. So we've got one star that's really massive, about 8 times the mass of the sun, and then a couple of other stars that are roughly about twice the mass of our sun. And the two smaller stars are in a system together. They're what's called a binary star, orbiting one another. The 8 solar mass star it's on its own, it's separate. And these stars probably form in a cluster like this. So this is what's called an open cluster. It's a bunch of relatively young stars that all form together. So our stars are located in some sort of very pretty cluster such as this. All right, so about 1 million years after they form, the stars are just kind of sitting there doing their thing. The two smaller stars are orbiting one another. All of them are converting hydrogen into helium. You know, nothing all that exciting is happening. Another 1 million years later, well, our bigger star has started to run out of hydrogen in its core, and now starts to take some of that helium and converts it into carbon and oxygen. So we're going from the kind of the simplest element in the universe to slightly more complex elements. So we keep following them along. 3 million years. Oh, what happened? Hold on. Let's go back to 2 million years. So we've got our 3 stars. We go a little bit further. Okay, so now we're 2.5 million years. Our big star started to run out of carbon and oxygen, or started to run out of helium in the core, and is now starting to form even heavier elements, magnesium and neon. We keep following it forward. It gets a little bit cooler. Take a drink. It gets a little bit cooler, a little bit bigger, and also starts forming even more heavy elements. So now it starts to form maybe silicon and sulfur and calcium, some of those intermediate mass elements. After that, it gets even a little bit cooler, and now starts to form iron in its core. So it's run through all those lower mass elements, and it starts to form iron. And iron is about as far as it's going to be able to go and maintain support for itself. So after this, in the core of the star, it starts to form nickel. But there's a problem, that once it tries to start to form nickel, forming nickel no longer gives it energy. So previously, all the elements, the fusion was giving more and more energy, or not more and more energy, but giving energy out as the process occurred, and that no longer happens. So our star starts to collapse. We start to lose heat and pressure inside the center of the star. And everything says, okay, well, you're not pushing me out, so I'm going to rush inward because gravity's really strong. And so that is where our neutron star forms. Essentially, things get so hot and dense in the center as everything starts trying to rush in, that things are no longer able to be supported. It overcomes quantum pressure, trivia question. It overcomes quantum pressure and starts to form the core of a neutron star. At the same time, it starts to form a lot of those other really, really heavy elements. So essentially, all those neutrons that form in the center of the star are able to move around and join up with other atoms and essentially form extremely, extremely, extremely heavy elements. So this is where we start to get a lot of, you know, things like uranium and gold and those very heavy elements essentially form during this part of the process. So in that moment, however, when the neutron star forms, it transitions from being something that has no pressure and no heat at the center to something that's really, really, really hard and provides a lot of pressure. To be honest, we don't actually fully understand this process. There's a lot of people working really hard on it, but this is one of the leading edges of our understanding of physics. In that process as well, if the star is massive enough, that neutron star can be squeezed down and start forming a black hole. So perhaps in the very, very, very center of the neutron star, a black hole starts to form, and that has, as far as we understand, no pressure in it. And so it can start feeding the black hole more and more. But we've already had that rebound from the formation of the neutron star. So that star starts to explode. So we no longer have a star. Now we've really truly got the start of a supernova. So what happens from there? All those outer layers get blown off, and we're left with just the neutron star or black hole that's down in the center. What happens is something like this. This is the Crab Nebula, also my very, very nice shirt. This is a remnant of a supernova that exploded about 1,000 years ago. And the question is, what are we seeing here? What are we learning, and how is this important? So this thing is already 11 light years across. It's really, really, really huge. Imagine the sun essentially spreading out over that great distance. All that pretty colors that you see, there's a lot of dust. So kind of the orangish and reddish colors are dust and hydrogen, and some of the materials from the outer layers of the star that are blown off. There's a lot of hot gas. And then down in the center of this particular one is a neutron star. So that dense core remnant of the star. Keep going on, that keeps expanding. It keeps going outward. So about 10,000 years after the explosion, it looks something like this. You can see now that there's a lot of stars that are kind of inside. It's expanded to cover a really huge area. There's some really pretty pictures that you can take of this. There's still a lot of dust, there's still a lot of gas, it keeps expanding. One of the most important things that's occurring at this stage is that material is crashing into other material that's out there in the galaxy. It's providing those metals and those heavy elements that are needed for the next generation of stars. In addition, it's providing a shock wave that's pushing through all the gas in the rest of the galaxy that helps the next generation of stars to form. So our solar system would not exist if it hadn't been for a supernova. We wouldn't exist if it hadn't been for supernova. So like I said before, all the iron and calcium and those heavy elements that are part of our bodies were in a supernova. They helped the solar system form, they helped the sun form, and the fact that the shock went through helped compress the clouds that allowed our solar system to form. All right, so let's move on. 3 million years. We no longer have our big star, but there's a black hole or maybe a neutron star that's sitting there in its place. But other two stars are still just sitting there doing their thing. So they're still just forming helium out of hydrogen. And we go on, and we go on, and on, and on, and on. All right, something happens. So about 1.5 billion years after they form, one of those stars was a little bit more massive than the other one, and it starts to form what we call a red giant. So it expands, it runs out of hydrogen in its core, it expands, it cools off. And starts forming carbon and oxygen. And if for our sun, this process is going to occur, and it's just going to kind of like run out its life and nothing more will occur. But there's this other guy right next to it who says, oh, you're done with all that hydrogen? I'll take some of it. So what we end up with is one star that's just what we call a white dwarf, and the other star takes over all that other material that it didn't want or didn't need, and forms a slightly more massive star. So it's still just an ordinary star, just a little bit more massive and a little bit hotter than it used to be. A little bit later, it's it was already kind of about near the end of its lifetime, so all that extra material helps speed it up, and it again reaches the red giant phase and starts to expand. And again, now it's got this companion right next to it that was sitting there not doing anything. And it says, oh, you're done with all that stuff? Well, I'll take some of it. So some of that material from the larger red giant transfers over to the white dwarf that had just been sitting there. And it starts building up. It forms a little bit more carbon and oxygen, and then it reaches this very special magic mass called the Chandrasekhar limit, about 1.4 times the mass of the sun. And now that white dwarf can no longer hold itself up. So that white dwarf would have just sat there if it didn't have a companion. But with the companion, material transferred over, and it reaches this magic mass and starts turning some of that carbon and oxygen into those heavier elements. This goes on for a very short period of time, about 100 years, and then for some reason, which we really don't understand at all, it explodes. So it goes from kind of relatively rapidly burning the stuff into detonation. It forms a lot of iron and nickel in this process. It's equivalent to this thermonuclear bomb, so we call these thermonuclear supernova. And boom, we no longer have a supernova. Or we no longer have a star. We have a supernova. So again, the material expands outward. It expands in a very, very spherical shell. So not a lot of structure. Compared to my shirt, the Crab Nebula, this is very, very round. We see again a lot of dust and hot gas that are released in this process. Much like the other supernova that we saw, this is going to sweep through the galaxy and do the exact same thing. It's going to provide the metals, the iron, calcium, and everything else that are required in the next generation of stars, and it's also going to help the next generation of stars form. There's one other thing that this particular type of supernova is very useful to us for. So the fact that they always are 1.4 times the mass of our sun when they explode is really helpful. It means that those stars are always the exact same brightness when they occur. So we can use this fact to understand how our universe is evolving. When we see things that are really distant, we don't know we don't necessarily know how far away they are based on their brightness. Something that's dim could be close by and appear bright, or something that's bright could be really far away and appear dim. So we can use these to understand, we know exactly how bright they are, so we can look at how dim they are, and we can also measure their redshift. So as light comes out of one of these supernova, we'll follow that light onward as it heads to Earth on the right side. And if we consider three possible universes, one in which there's no expansion, one in which there's a constant expansion, and one in which there's this thing called dark energy, we'll see a difference in the light when it arrives at Earth. So under no expansion, the light looks exactly as it did when it left that star. Under constant expansion, the light gets a little bit spread out, what we call redshifted. And under dark energy case, the light could potentially be more redshifted as over the same amount of time that the light is traveling. So we can measure this effect and detect, and this is exactly how dark energy was first detected, by looking at exactly these type of thermonuclear supernova and saying, oh, this light does not look the way that we expect it to based on how bright we see these objects to be. And we said, okay, well, it doesn't match with the constant expansion theory, so there must be this mysterious thing called dark energy that's causing our universe to expand faster and faster over time. So these supernovae are critical to understanding dark energy just on the basis of how they cause the light to get stretched as the light's moving towards us. All right, so back to my summary. Supernova are extremely important in our understanding of the universe, understanding of physics. They probe the very high energy realm of physics. They're factories for these things called neutron stars and black holes, which we still really don't understand how these things form, but we know just enough of what's going on to say that yes, these conditions in supernova are the only way in which these things can occur. Elements heavier than oxygen, all that iron and calcium are formed in those late stages of the massive stars, as well as in that burning process of the thermonuclear supernova. And then thermonuclear supernova tell us about the presence of dark energy that we otherwise wouldn't be able to detect in the universe. So thank you very much. I will take questions.
Dr. Brian Mulligan.
Still getting used to that title.
So we'll take a few questions. What we'll do is, you have a question, raise your hand. I will call on you. You'll ask the question. One of us will hopefully remember to repeat the question, and then Brian will answer it. So how about we start with this person right here?
So all suns are thermonuclear reactions. So a supernova and a thermonuclear supernova are almost by definition the same thing. So what is really special about a thermonuclear supernova?
So the question is, stars are all thermonuclear furnaces, and supernova have all these reactions going in them. Why is a thermonuclear supernova kind of special or different than just the processes that are normally going on? And it's largely about the detonation. So in a star like the sun, there's fusion that's going on constantly, converting hydrogen into helium. Even in the massive stars, there's these similar processes. In a thermonuclear supernova, that process runs away. It goes from being a steady state thing that's just barely supporting the star to this rapid process that suddenly explodes. So if the older people here might remember knocking in your car engine when your car goes from running smoothly into this like where there's sudden explosion inside the cylinders, which is what you really don't want to have happen. And it's a similar sort of thing in these thermonuclear supernova. It goes from a steady state burning phase to this sudden explosion that just completely destroys everything.
All right, how about this person in the front?
Sorry.
What effect, if any, does the supernova have on the star?
Okay, so that's a really great question. What effect does the supernova have on the companion star? And I know we're going to be talking about this during news today too, which I was really excited to see. The companion survives. So the companion star, a little bit, about 1/10 of a solar mass or so of the material gets stripped off the outer edge. But the companion star should just more or less keep going on doing whatever it was doing beforehand. And there's searches that are currently ongoing to try to find these companion stars. So far, we have not found any. There is one supernova remnant that occurred that Tycho observed. Tycho observed the supernova about 500 years ago. We're looking for the companion star in that remnant. There's a couple of potential stars that might be that companion star, but there's nothing definitive so far, and it's still very controversial. But for the most part, we have not found a single one of these remnants.
All right, let's hear a question from the balcony. So go right there.
How do you tell that light is dimmer than it should be if it's not yet further away?
Okay, so the question is, when we're observing these really distant thermonuclear supernovae, and how can we tell that there's a difference using these as standard candles? How do we tell the difference between what's expected and what we see? And there's kind of two answers. So one, we know fundamentally how bright these supernova are. So given how far we expect the light to travel, there's a certain amount of brightness and redshift that we expect to see when we see one of these things really far away. The second part of it is Einstein. So Einstein gave us general relativity. He gave us this set of equations of understanding how the universe evolves and expands over time. And we can add different pieces into that. We can take into account how much material is in the universe, how much light is in the universe, how much curvature or this weird fundamental, if our universe is not flat, if it's more like Earth-shaped or something weird, we know how much that can affect. And then we can also add in how much of an effect Einstein's original cosmological constant, or what we call now dark energy, or whatever the heck that is. We understand how much that will affect the brightness and redshift simultaneously of these supernova. And when we see the brightness and we measure the redshift at the same time, with the constant with the constant expanding universe, or kind of general understanding of what we normally expect with what we know of in the universe, there's a noticeable discrepancy between what the redshift is and what the brightness is for the model of the expected expansion or constant expansion or dark energy. And we can say that yes, there must be dark energy present in order to explain both the redshift and the brightness at the same time.
All right, let's do one more question. The person right at the end has been patiently having his hand raised.
So, you showed how first hydrogen goes to helium, and then helium proceeds on to carbon and other elements. Why does the helium, as soon as it's starting to form, starts undergoing fusion reactions, successively heavier things start forming fusion reactions? Why does it have this whole time span in creating such rapid compression?
So the question is why does the evolution of what the star is forming take time? Why doesn't it start forming helium, and then why doesn't helium just immediately start forming into all the other elements and not only just carbon and oxygen? And essentially the temperatures and densities that are required to form the heavier elements, it requires it getting successfully hotter and more dense in order to form those heavier elements. So our sun can form helium because the temperature and density in the core of the sun are just right for converting hydrogen into helium. Helium requires a higher temperature to go to carbon and oxygen, simply because helium has more protons in the core, and they're more likely to repel one another. It takes more energy to get them to run into each other, essentially. And to build those heavier and heavier elements, you're dealing with atoms that have more and more protons in them, so they're resisting more and more that process of forming something heavier. So you need the helium can start forming carbon and oxygen. It releases heat and helps the star stabilize again. And then once it runs out of that helium, there's no longer anything to keep it stable, so it compacts, gets a little bit hotter and a little bit more dense, and that phase allows it, to start forming silicon, say, or magnesium, and then that runs out of the next phase, and it has to get a little bit more hot and dense to go on the next phase, and so on.
I have a question. So after spending 5+ some number larger than 5 years of studying this in grad school, and now being Dr. Mulligan, still find supernova exciting?
They're really cool. It's actually one of the other interesting facts. I don't know if Craig even knows this. My advisor is here in the back of the room. When I came into grad school, I was absolutely certain that I did not want to work on supernova. Fortunately, Craig changed my mind. But what I love most is understanding how our universe works. And these are one of the best probes for understanding how the highest energy processes in the universe work. These crazy ideas, like how black holes form, how quantum mechanics works at this like weird relativistic high energy level. Yeah, supernova are still really cool.
Brian will be around at intermission after the show. Astrobit, everyone.
Thank you.